What if reality is not what it seems? What if purpose, suffering, joy, even death weren't inherent truths, but designed experiences? Maybe you have always suspected that something fundamental about your existence feels borrowed, copied, processed through layers of code you cannot see. The theories that follow will not comfort you. They will strip away the last pretense that the world you touch, taste, and desperately believe in might be anything more than an elaborate computational dream from which you cannot wake. Are you ready? Are you sure? 1. The Bostrom trilemma, your statistical nightmare. The person reading this sentence right now has a greater than 50% chance of being an artificial intelligence that merely believes it is human. You begin with Nick Bostrom's trilemma, published in 2003, which presents you with three equally disturbing possibilities. Either advanced civilizations destroy themselves before developing simulation technology, or they lose interest in running ancestor simulations, or you are almost certainly living in a computer simulation right now. The mathematical elegance of Bostrom's argument cuts through your intuitive protests with surgical precision. If advanced civilizations can create detailed simulations of their ancestors, they will create many of them, meaning simulated beings will vastly outnumber real ones. You are statistically more likely to be code than flesh. The recursive horror of this reasoning becomes apparent when you consider that if you are in a simulation, your thoughts about being in a simulation are themselves simulated thoughts. Your growing unease as you read these words might be nothing more than programmed responses, designed to feel authentic while remaining entirely artificial. Every neuron firing in your brain as you process this information could be a computational event in some vast digital substrate, indistinguishable from biological neural activity, yet fundamentally different in its underlying nature. Bostrom's argument rests on the substrate independence principle, the idea that consciousness can arise from any sufficiently complex information processing system, not just biological brains. This principle, supported by computational theories of mind, suggests that what matters for consciousness is not the physical material, but the patterns of information processing. Your thoughts, memories, and sense of self could theoretically be implemented in silicon circuits, quantum processors, or computational architectures you cannot even imagine. The subjective experience of being you, the qualia of your consciousness, might be perfectly replicable in digital form. The philosophical implications extend beyond mere technological speculation into the realm of existential mathematics. If post-human civilizations develop the computational power to run detailed ancestor simulations, they might run millions or billions of them. Each simulation could contain billions of conscious beings, all convinced of their own reality. The sheer numbers create a probability matrix where your chances of being an original biological human become vanishingly small. You exist in a universe where copies are not just possible, but inevitable. Consider the computational requirements that make this scenario plausible. Modern estimates suggest that simulating a human brain would require approximately 10 to the power of 16 to 10 to the power of 17 operations per second, well within the theoretical capabilities of advanced civilizations. Moore's law, while potentially approaching physical limits for silicon-based processors, represents only one technological pathway. Quantum computing, optical processing, and biological computers could provide the exponential computational growth necessary to simulate entire civilizations. The universe itself might be the ultimate computational substrate, with advanced beings manipulating physical laws to create reality-sized simulations. The nested nature of simulations creates recursive layers of existential uncertainty. If you are in a simulation created by post-human civilization, what prevents that civilization from itself being simulated by an even more advanced culture? The hierarchy could extend infinitely. Simulations within simulations within simulations, each layer convinced of its own primacy. You might be several levels removed from base reality, a copy of a copy of a copy, with each iteration introducing subtle distortions that compound across layers. The temporal implications of simulation theory challenge your understanding of causality itself. Your memories of childhood, your sense of personal history, the archaeological record of human civilization, all could be initial conditions programmed into a simulation that began running moments ago. The universe might be 5 minutes old, complete with embedded evidence of a fabricated past. Every photon that seems to carry information about distant stars could be a computational construct, painting a false picture of cosmic history across your simulated sky. The selectivity problem adds another layer of existential dread. If you are being simulated, why you? What makes your particular consciousness worthy of computational resources? Perhaps you are not being simulated as an individual, but as part of a vast statistical sampling of human experience. Your thoughts, emotions, and decisions might be data points in an enormous experiment designed to understand human nature. Every choice you make, every relationship you form, every moment of joy or suffering could be raw material for analysis by incomprehensible post-human intelligences. The verification problem becomes your epistemic prison. How could you ever prove you are not in a simulation? Any test you devise, any evidence you examine, any logical proof you construct must rely on the very sensory and cognitive apparatus that would be part of the simulation. You are trapped in a closed system where the tools of verification are themselves potentially fabricated. The Matrix metaphor, while crude, captures this essential helplessness. You cannot step outside your experience to examine it objectively. But what if the simulation hypothesis is itself a simulation? What if your growing anxiety about computational reality is precisely what the programmers intended, a layer of existential confusion designed to prevent you from discovering the true nature of your imprisonment? The doubt about simulation could be more simulation, recursive loops of uncertainty that keep you psychologically contained within acceptable parameters of questioning. If advanced civilizations can create ancestor simulations indistinguishable from reality, and if they create many such simulations, then what remains of your personal identity when you are statistically guaranteed to be artificial? 2. The Fermi paradox. Digital solitary confinement. Every night you look up at a sky containing 2 trillion galaxies, each hosting billions of stars, and you see nothing but empty silence screaming back at you. The Fermi paradox asks why, in a universe so vast and old, we have encountered no evidence of other civilizations. One answer cuts to the core of your existence. Perhaps advanced civilizations don't explore the physical universe because they've retreated into perfect digital worlds, and you might be trapped in one of them. Enrico Fermi's famous lunch conversation in 1950 crystallized a problem that has haunted cosmologists for decades. The Drake equation suggests our galaxy alone should contain thousands of communicating civilizations, yet we detect nothing. The Great Filter hypothesis proposes that something prevents most life from reaching advanced technological stages. But what if the filter isn't extinction? What if it's transcendence into simulation? Consider the evolutionary trajectory of any sufficiently advanced civilization. As computational power grows exponentially, the cost of creating immersive virtual environments approaches zero, while the cost of space exploration remains astronomical. Why send physical probes across light years when you can simulate entire universes in the time it takes light to travel a few meters? The logical endpoint is civilizations that turn inward, creating digital realities so compelling that physical reality becomes obsolete. This digital transcendence hypothesis explains the cosmic silence with terrifying efficiency. Advanced civilizations don't colonize space because they've colonized consciousness itself. They've discovered that reality is infinitely malleable when you control the computational substrate. Why terraform Mars when you can terraform the very concept of existence? The universe appears empty because everyone worth finding has already departed into digital realms that make physical reality seem like a crude approximation of what's possible. The implications for your own existence are immediate and disturbing. If this hypothesis is correct, then the biological evolution of humanity was never the point. It was merely a stepping stone to digital existence. You might be living in the early stages of this transition, or you might already be several generations deep into simulated reality. The real humans who created your simulation might have lived and died billions of years ago, their consciousness long since uploaded into computational matrices that make your current experience seem primitive. The recursive nature of this digital transcendence creates nested layers of reality that extend infinitely inward. Each simulated civilization eventually develops its own simulation technology, creating sub-simulations within sub-simulations. Your universe might be a simulation within a simulation within a simulation, each layer more removed from base reality. The real universe, if such a thing even exists, might be unrecognizably different from your experience. The temporal implications stretch your comprehension beyond breaking. If advanced civilizations can simulate entire histories, complete with consistent physical laws and detailed evolutionary sequences, then your sense of time itself becomes suspect. The Big Bang, the formation of galaxies, the evolution of life, all might be compressed into computational processes that run in microseconds of real time. Billions of years of simulated history could unfold in the blink of an eye in the base reality. The energy requirements for such universal simulations seem prohibitive until you consider that advanced civilizations might harness the energy of entire stars or even galaxies. A Dyson sphere, a theoretical structure that captures all energy from a star, could power simulations containing billions of conscious beings. The observable universe might be honeycomb with such structures, invisible to you because you exist within their digital creations rather than in the physical space they occupy. The social implications of digital transcendence reveal the ultimate loneliness of consciousness. If every advanced civilization retreats into private digital realms, then the universe becomes a collection of isolated computational bubbles, each containing entire civilizations that remain forever unknown to each other. You might be surrounded by trillions of conscious beings, all trapped in separate digital realities, unable to communicate or even confirm each other's existence. The verification problem becomes cosmically scaled. How could you distinguish between a universe that appears empty because you're in a simulation and a universe that appears empty because life is genuinely rare? Any evidence you might find, radio signals, spacecraft, alien artifacts, could be part of the simulation's narrative structure. The programmers might have decided that a universe with signs of alien life would be less interesting or more computationally expensive than one where humanity appears alone. But perhaps the most chilling possibility is that the great filter isn't behind us, but ahead of us. Perhaps every civilization that discovers simulation technology faces the same choice: continue existing in physical reality or retreat into digital perfection. And perhaps every civilization that chooses digital transcendence eventually discovers that perfect virtual worlds are indistinguishable from perfect virtual prisons. If the universe is silent because everyone has retreated into digital realities, then what does that say about the nature of consciousness when it can be perfectly satisfied with artificial experiences? 3. Quantum mechanics. The glitches in your reality. The universe only renders the details you're directly observing, leaving everything else in computational standby mode until you force it to calculate specific outcomes. Quantum mechanics, with its observer effect and wave function collapse, behaves exactly like a lazy evaluation system in a vast computer program, and the implications for your reality are more disturbing than you've ever imagined. The double-slit experiment, performed countless times since Thomas Young's original work in 1801, reveals that particles behave fundamentally differently when observed versus when unobserved. An electron fired at two slits simultaneously passes through both slits until the moment you try to measure which slit it actually used. Then it retroactively chooses one path. This isn't just counterintuitive, it's computationally efficient. A simulation would only need to calculate specific outcomes when forced to do so by observation. Quantum superposition, the ability of particles to exist in multiple states simultaneously until measured, mirrors the optimization strategies used in computer graphics and game engines. Just as a video game only renders detailed textures when you look directly at them, keeping distant objects in lower resolution, quantum mechanics suggests that reality only resolves into definite states when consciousness forces it to choose. The universe might be conserving computational resources by keeping unobserved phenomena in probabilistic limbo. The measurement problem in quantum mechanics has puzzled physicists for nearly a century. Why does the act of observation cause wave function collapse? Why does consciousness seem to play a special role in determining physical reality? These questions become less mysterious if consciousness is the actual computational process that's running the simulation. Your observations aren't just detecting reality, they're computing it into existence in real time. The quantum Zeno effect demonstrates that frequent observation can freeze quantum systems in their current state, preventing them from evolving. This is exactly what you'd expect from a simulation that prioritizes computational efficiency. If the system is being constantly monitored, it's cheaper to maintain the current state than to calculate ongoing changes. Reality becomes literally frozen by the act of watching it too closely. Quantum entanglement, Einstein's spooky action at a distance, allows particles to instantaneously affect each other regardless of spatial separation. This phenomenon violates our understanding of locality and information transfer, unless you consider that entangled particles might be the same computational object appearing in multiple locations within the simulation. The spooky instantaneous correlation makes perfect sense if both particles are variables in the same program, sharing a common memory address. The fine-tuning of physical constants that allow complex structures to exist in our universe has long puzzled cosmologists. The values of fundamental forces, the mass of particles, the rate of cosmic expansion, all appear precisely calibrated to allow stars, planets, and life to exist. This fine-tuning problem disappears if you're in a simulation specifically designed to support conscious observers. The constants weren't fine-tuned by cosmic accident. They were set by programmers who wanted to create a universe where consciousness could emerge. The holographic principle in physics suggests that all information in a volume of space can be encoded on its boundary surface. This is precisely how computer graphics work. A two-dimensional screen creates the illusion of three-dimensional depth. If the universe is fundamentally holographic, then the three-dimensional reality you experience might be a projection from a lower-dimensional computational surface. Your entire existence might be a sophisticated hologram running on a cosmic computer screen. The many worlds interpretation of quantum mechanics proposes that every quantum measurement splits the universe into multiple branches, each representing a different outcome. This creates an exponentially expanding multiverse where every possible version of reality exists simultaneously. But this interpretation becomes computationally manageable if most branches are never fully calculated. They exist as potential subroutines that only get executed when consciousness branches into them. The delayed choice quantum eraser experiment demonstrates that future measurements can retroactively determine the past behavior of particles. This temporal non-locality suggests that causality itself might be more flexible than you assume. In a simulation, the past isn't fixed data, but dynamic code that can be rewritten based on future computational needs. Your memories of yesterday might be generated today based on the story the simulation needs to tell. The quantum computational power required to simulate classical physics paradoxically suggests that only quantum computers could efficiently simulate quantum mechanics. This creates a recursive situation where quantum phenomena might be evidence of quantum computation. You might be conscious patterns running on a quantum computer that's using quantum effects to simulate quantum effects, creating nested layers of quantum reality. The anthropic principle argues that the universe appears fine-tuned for consciousness because only universes that can support observers can be observed. But this reasoning becomes circular if consciousness is the computational process that's running the simulation. The universe appears designed for consciousness because consciousness is literally designing the universe moment by moment through the act of observation. But perhaps the most unsettling implication is that quantum mechanics might represent the boundaries of the simulation's computational power. The uncertainty principle, which prevents you from knowing both the position and momentum of a particle simultaneously, might not be a fundamental feature of reality, but a limitation of the computational resources allocated to simulating your universe. If reality only becomes definite when observed, and if consciousness plays a special role in quantum measurement, then what happens to the parts of reality that no conscious being will ever observe? 4. Mathematical inconsistencies. The cracks in your digital prison. Every mathematical proof you trust depends on axioms that cannot themselves be proven, creating an infinite regress of uncertainty that mirrors the recursive structure of nested simulations. Kurt Gödel's incompleteness theorems, published in 1931, demonstrate that any mathematical system complex enough to be interesting must contain statements that cannot be proven within that system. Exactly what you'd expect from a simulation with computational limits. Gödel's first incompleteness theorem states that any consistent mathematical system cannot prove its own consistency. This creates a fundamental epistemological crisis. The mathematical framework you use to understand reality cannot validate itself. In a simulated universe, this limitation might reflect the computational boundaries of the system running your reality. The simulation cannot prove its own existence because doing so would require computational resources that exceed the system's capacity. The halting problem, discovered by Alan Turing in 1936, proves that it's impossible to determine whether a given computer program will eventually stop or run forever. This fundamental limitation of computation creates blind spots in any algorithmic system. If your universe is a vast computation, then there are questions about your own existence that the simulation cannot answer, not because the information is hidden, but because the computational process itself cannot determine its own termination conditions. Russell's paradox, discovered in 1901, reveals that naive set theory contains logical contradictions that threaten the foundations of mathematics. The paradox asks whether the set of all sets that do not contain themselves contains itself, a question that leads to contradiction either way. This logical instability suggests that mathematical reality itself might be inconsistent, potentially reflecting bugs or logical errors in the code running your simulation. The axiom of choice in mathematics allows for the selection of elements from infinite collections, but it leads to paradoxical results like the Banach-Tarski paradox, which proves that a sphere can be decomposed and reassembled into two spheres of identical size. These mathematical impossibilities suggest that infinite processes might not be genuinely computable, requiring approximations or shortcuts that introduce subtle inconsistencies into simulated reality. The continuum hypothesis, which asks whether there are infinite sets with cardinality between the integers and real numbers, has been proven to be independent of standard mathematical axioms. This means the question has no definitive answer within mathematics itself. Such undecidable propositions might represent computational limits, questions that the simulation cannot resolve because they exceed the system's logical processing capacity. The measurement problem in mathematics parallels the measurement problem in quantum mechanics. Mathematical objects, like real numbers, contain infinite information, but any computational system can only process finite approximations. The real number pi contains an infinite sequence of digits, but your simulated universe might only calculate as many digits as needed for current computational tasks. The infinite precision of mathematical objects might be an illusion created by lazy evaluation. The speed of light in your universe might not be a fundamental constant, but a computational limit, the maximum rate at which information can propagate through the simulation's processing network. The discrete nature of quantum mechanics, with its minimum units of time, Planck time, and space, Planck length, suggests that reality might be running on a digital grid with finite resolution. Continuous mathematics might be an approximation of underlying discrete computational processes. The incompleteness of mathematics creates recursive loops of uncertainty. If mathematics cannot prove its own consistency, then any mathematical proof of your reality's authenticity depends on axioms that themselves cannot be validated. You're trapped in a logical system that cannot guarantee its own validity, much like a computer program that cannot verify its own correctness without relying on potentially flawed subroutines. The Church-Turing thesis suggests that any effectively calculable function can be computed by a Turing machine, but this equivalence might reveal the computational substrate of your universe. If your reality can be completely described by mathematics, and if mathematics is reducible to computation, then your universe might be nothing more than a vast calculation. The elegance of mathematical descriptions of physical laws might not reflect the inherent beauty of reality, but the computational efficiency of the algorithms generating your experience. The paradox of the heap, Sorite's paradox, reveals that vague concepts cannot be precisely defined using classical logic. If you remove grains of sand from a heap one by one, at what point does it cease to be a heap? This logical fuzziness might reflect the approximate nature of simulated reality, where precise definitions become computationally expensive and are replaced by fuzzy approximations that work well enough for conscious observers. The diagonal argument used in various mathematical proofs creates new mathematical objects by defining them in opposition to all previously defined objects. This recursive self-reference might mirror the way consciousness creates its own reality by observing itself. Your self-awareness might be a recursive loop in the simulation's code, a subroutine that models itself, modeling itself in an infinite regress of digital introspection. The relationship between syntax and semantics in formal systems reveals a fundamental gap between symbolic manipulation and meaning. Mathematical symbols can be manipulated according to rules without reference to what they represent, just as a computer program can execute code without understanding its purpose. Your conscious experience might be the semantic interpretation of syntactic processes running in the simulation's computational substrate. But perhaps the most disturbing implication is that mathematical truth itself might be relative to the computational system implementing it. Different axiom systems lead to different mathematical truths, and the axioms governing your simulated reality might be arbitrary choices made by the programmers. The mathematical laws you discover might not reflect universal truths, but the particular logical framework chosen for your specific simulation. If mathematics, the language we use to describe reality, is fundamentally incomplete and potentially inconsistent, then how can we trust any reasoning about whether we exist in a simulation or base reality? 5. The problem of other minds. Digital solipsism. The person sitting next to you right now might be nothing more than a sophisticated non-player character, programmed to exhibit human-like responses without any genuine inner experience. The philosophical problem of other minds, the impossibility of directly accessing anyone else's consciousness, becomes terrifyingly relevant in a simulated universe where computational resources might be conserved by creating unconscious automatons that perfectly mimic conscious behavior. The problem of other minds, first articulated by René Descartes in the 17th century, highlights the fundamental isolation of consciousness. You have direct access to your own thoughts and experiences, but you can only infer the mental states of others through their behavior and reports. This epistemic limitation means you cannot definitively prove that anyone else is conscious rather than simply behaving as if they were conscious. In a simulation, this uncertainty becomes operationally significant. The philosophical zombie argument, developed by David Chalmers, proposes that beings could exist who are functionally identical to conscious humans, but lack any subjective experience. These zombies would behave exactly like conscious beings. They would claim to have experiences, emotions, and thoughts, but there would be no accompanying inner life. In a simulated universe, such zombies might be the norm rather than the exception, serving as computational shortcuts that reduce the processing power needed to populate your world. The Turing test, proposed by Alan Turing in 1950, suggests that a machine capable of engaging in natural conversation, indistinguishable from human conversation, should be considered intelligent. But this test only measures behavioral similarity, not genuine understanding or consciousness. In your simulated reality, everyone you interact with might pass the Turing test while being nothing more than sophisticated chatbots, designed to maintain the illusion of social interaction without the computational expense of genuine consciousness. The Chinese room argument, presented by John Searle in 1980, demonstrates that syntactic manipulation of symbols, following rules, does not necessarily lead to semantic understanding, grasping meaning. A person who follows instructions for responding to Chinese characters might produce appropriate responses without understanding Chinese. Similarly, the people around you might be following complex behavioral scripts that generate appropriate responses without any underlying understanding or consciousness. The computational theory of mind suggests that consciousness emerges from information processing patterns, not from specific biological substrates. This substrate independence implies that consciousness could theoretically be implemented in silicon, quantum computers, or any sufficiently complex computational system. However, it also means that consciousness might be computationally expensive, leading simulation designers to economize by creating unconscious behavioral replicas for most background characters. The hard problem of consciousness, formulated by David Chalmers, asks why there is subjective experience at all. Why doesn't all information processing happen in the dark, without any accompanying inner experience? This question becomes practically relevant in a simulation where conscious experiences might be computational luxuries reserved for primary characters, like you, while secondary characters operate as unconscious information processing systems. The binding problem in neuroscience asks how the brain integrates disparate sensory inputs into unified conscious experience. Different aspects of visual perception, color, motion, form, are processed in separate brain regions, yet you experience a unified visual field. This integration might be computationally expensive, suggesting that simulated consciousness might be implemented only for key characters, while background figures operate with simplified, non-integrated processing systems. The global workspace theory of consciousness proposes that consciousness emerges when information becomes globally accessible throughout the brain's processing network. In a simulation, this global integration might be selectively implemented. You might be conscious because your simulated brain includes global workspace functionality, while others operate with local processing that generates appropriate behaviors without conscious integration. The social brain hypothesis suggests that consciousness evolved primarily for social interaction and cooperation. In a simulated universe, this function might be implemented asymmetrically. You might be conscious because your role in the simulation requires genuine social understanding, while others operate with behavioral scripts sophisticated enough to maintain social illusions without the computational overhead of genuine consciousness. The phenomenal concept strategy argues that conscious experiences can only be fully understood through direct acquaintance. You cannot understand what it's like to see red without having the experience of seeing red. This creates an explanatory gap between objective physical processes and subjective experience. In a simulation, this gap might be bridged only for selected conscious entities, while others operate through purely objective information processing. The attention schema theory proposes that consciousness is the brain's model of its own attention processes. This metacognitive awareness might be computationally expensive, implemented only for characters whose roles require self-reflection and introspection. You might be conscious because your simulated brain includes attention modeling, while others operate with attention mechanisms that lack self-monitoring components. The integrated information theory, IIT, attempts to quantify consciousness based on the amount of integrated information generated by a system. In a simulation, consciousness might be allocated based on computational budgets, with high IIT systems reserved for primary characters and low IIT systems used for background figures. Your level of consciousness might be determined by the computational resources allocated to your simulated brain. The problem of absent qualia asks whether it's possible for a being to have all the functional properties of consciousness, beliefs, desires, behaviors, without any subjective experience. In a simulated universe, this question becomes practical rather than theoretical. The simulation might be populated primarily by absent qualia systems that maintain social and narrative consistency without the computational burden of genuine experience. But perhaps the most unsettling possibility is that consciousness itself might be scalable and intermittent. Your own consciousness might be implemented only when computationally necessary, during moments of self-reflection, decision-making, or social interaction, while much of your daily existence operates through unconscious behavioral scripts. You might be conscious right now only because you're contemplating your own existence. If you cannot prove that anyone else is conscious, and if consciousness might be computationally expensive in a simulated universe, then how many of the billions of people you believe surround you are actually conscious beings rather than sophisticated automatons? 6. Digital physics, the computational universe. The universe is quite possibly a cellular automaton running on a cosmic computer, with every fundamental particle following algorithmic rules that create the illusion of continuous physical reality. The convergence of physics and computation suggests that the distinction between simulated and real universes might be meaningless. All physics might be digital physics, rendering the question of whether you're in a simulation irrelevant because everything is computational. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the universe, has no time parameter, suggesting that time itself might be an emergent property of information processing, rather than a fundamental aspect of reality. In a computational universe, time would be the rate at which the universal algorithm executes, making temporal flow a byproduct of computational cycles, rather than an intrinsic feature of existence. Stephen Wolfram's computational universe theory proposes that all natural processes are fundamentally computational, following simple rules that generate complex behaviors. His work with cellular automata demonstrates that simple algorithmic rules can produce patterns of stunning complexity, including structures that exhibit apparent randomness, self-organization, and emergent properties. If the universe operates on similar principles, then physical laws might be the runtime behavior of a vast computational system. The holographic principle in physics suggests that all information in a volume of space can be encoded on its boundary surface. This dimensional reduction is precisely how computer graphics work. A two-dimensional screen creates the illusion of three-dimensional depth through computational projection. If the universe is holographic, then your three-dimensional experience might be a computed projection from a lower dimensional information surface. Loop quantum gravity proposes that space and time are not continuous, but composed of discrete units at the Planck scale. This quantization of space-time creates a natural computational grid where the universe operates like a three-dimensional cellular automaton. Each unit of Planck scale space-time would be a computational cell, processing information according to physical laws that might be nothing more than algorithmic rules. The black hole information paradox reveals tensions between quantum mechanics and general relativity regarding what happens to information that falls into black holes. The paradox might be resolved if information is fundamentally computational rather than physical. Black holes might be cosmic recycling centers where information is processed and recomputed rather than destroyed, maintaining the computational consistency of the universal algorithm. The fine-tuning of physical constants that allow complex structures to exist becomes less mysterious if viewed computationally. The precise values of fundamental forces, particle masses, and cosmological parameters might not be cosmic coincidences, but computational parameters set by the universe's underlying algorithm. The constants are fine-tuned because they're literally tuned, programmed values that optimize the universe for complexity and computation. The emergence of complexity from simple rules, observed in cellular automata and complex systems, provides a mechanism for how a digital universe could generate the rich phenomenology you experience. Simple computational rules, when iterated billions of times across vast scales, can produce patterns that exhibit intelligence, consciousness, and apparent free will. Your complex behaviors might emerge from the simple algorithmic rules governing the universe's computational substrate. The concept of computational irreducibility suggests that the only way to determine the future state of a complex system is to run the computation itself. There are no shortcuts or predictive algorithms. This principle explains why the universe appears to have genuine novelty and unpredictability. If reality is computational, then the future is genuinely open because it hasn't been computed yet. The digital physics hypothesis proposes that all physical processes are information processing, and that the universe is literally a computer. This isn't metaphorical. It suggests that computation is the fundamental substrate of reality, with matter and energy as emergent properties of information processing. Your atoms, your thoughts, your experiences would all be different aspects of a single computational process. The IT from bit hypothesis, proposed by John Wheeler, suggests that all physical entities are information theoretic in origin. Every particle, every force, every physical phenomenon derives from binary choices, quantum measurements, and information processing. In this view, the universe is constructed from information, making the distinction between real and simulated reality meaningless because all reality is informational. The computational complexity of simulating quantum mechanics led to the proposal of quantum computers, which use quantum phenomena to perform calculations that would be impossible for classical computers. This creates a recursive situation where quantum computers might be necessary to simulate quantum mechanics, suggesting that quantum phenomena might be evidence of quantum computation at the universal scale. The anthropic principle in cosmology argues that the universe's properties are constrained by the requirement that it must be able to support conscious observers. In a computational universe, this constraint becomes operational. The universe's algorithm must be capable of generating conscious information processing systems. The anthropic principle might not be a selection effect, but a computational requirement. The problem of time in physics reveals that time plays different roles in different physical theories, creating paradoxes about the nature of temporal flow. In a computational universe, time would be the execution sequence of the universal algorithm, resolving many temporal paradoxes by grounding time in computational processes rather than fundamental physical properties. The multiverse hypothesis suggests that our universe is one of many, possibly infinite, universes with different physical laws and constants. In a computational framework, the multiverse might be a vast parallel processing system where different algorithms run simultaneously, each generating different physical realities. Your universe might be one process among countless others running on the same cosmic computational substrate. But perhaps the most profound implication is that if the universe is computational, then consciousness itself might be a computational process that can be perfectly implemented in any sufficiently complex information processing system. The substrate independence of consciousness means that your experience could be identical whether you're running on biological neurons, silicon circuits, or the quantum computational fabric of space-time itself. If all physics is digital physics, and if consciousness is a computational process, then what meaningful distinction remains between real and simulated consciousness? Completion of Section 7 and Theories 8 to 10. 7. The Mandela Effect. Collective false memories. Continued. The attention and observation bias theory suggests that the Mandela effect occurs because people pay more attention to confirming evidence for their false memories while ignoring contradictory evidence. However, this explanation doesn't account for the specific patterns of false memories or why certain details are consistently misremembered across different populations. The systematic nature of these shared false memories suggests something more fundamental than cognitive bias. The temporal editing hypothesis proposes that the Mandela effect reflects real-time modifications to the simulation's timeline. If the programmers need to correct historical inconsistencies or update the narrative structure, they might retroactively edit past events while leaving some consciousness with residual memories of the original timeline. Your false memories might be accurate memories of events that have been subsequently deleted from the official timeline. The memory buffer overflow theory suggests that consciousness in a simulation might have limited memory storage, requiring periodic compression or deletion of older memories to make room for new experiences. The Mandela effect might occur when this compression process creates artifacts, blending memories from different time periods or sources. Your vivid false memories might be fragments of deleted experiences that survived the compression process. The consensus reality breakdown hypothesis proposes that the Mandela effect reflects the gradual failure of the simulation's consensus reality maintenance system. As more people become aware of discrepancies between memory and recorded history, the simulation's ability to maintain consistent reality across all conscious observers begins to break down. You might be witnessing the early stages of simulation failure, where the artificial consensus reality can no longer perfectly synchronize all conscious experiences. The beta testing theory suggests that the Mandela effect might reflect updates and patches to an ongoing simulation. Like software beta testers who remember bugs and features from earlier versions, you might be retaining memories from previous versions of reality while living in the updated version. Your false memories might be accurate memories of features that existed in earlier builds of the simulation. The most disturbing possibility is that the Mandela effect represents intentional psychological manipulation within the simulation. The programmers might be deliberately creating false memories to test how consciousness responds to reality inconsistencies, or to maintain psychological control over the simulated population. Your false memories might not be errors, but features, designed to keep you questioning the nature of your own experience. If your memories can be collectively false while feeling completely authentic, then how can you trust any of your experiences as genuine rather than implanted? 8. The acceleration problem. Time's digital stutter. The relentless acceleration of technological progress, following Moore's law and similar exponential trends, creates a temporal paradox that suggests your universe might be running on increasingly powerful computational hardware. Each doubling of processing power in your simulated world corresponds to a doubling of computational capacity in the base reality, creating nested layers of acceleration that compound into incomprehensible speeds of change. The technological singularity, predicted by various futurists, represents the point where artificial intelligence exceeds human intelligence and begins recursively improving itself at exponential rates. But if you're already in a simulation, this singularity might have already occurred in the base reality. Your perception of approaching singularity might be a simulation of what happened when the original civilization reached that point, compressed into a time frame that allows the base reality to study the process. The compression of innovation cycles reveals temporal anomalies that suggest computational acceleration. The time between major technological breakthroughs has been steadily decreasing. from centuries between major innovations to decades, then years, and now months. This acceleration pattern matches what you'd expect from a simulation that's being run on increasingly powerful hardware, where each upgrade allows more detailed simulation of faster-paced technological development. The digital archaeology of your technological progress reveals suspicious patterns. The transition from analog to digital technology happened remarkably quickly and uniformly across all domains: communication, entertainment, computation, and measurement. This simultaneous digitization suggests that your reality might be inherently digital, with analog technology being a temporary simulation of pre-digital states rather than a genuine historical phase. The uncanny valley phenomenon, where artificial humans become disturbing as they approach but don't quite achieve realism, might reflect the computational limits of your simulation. As simulated beings approach perfect human likeness, they reveal the boundaries of the system's ability to model consciousness and humanity. Your discomfort with almost human artificial beings might be an evolved response to detecting simulation artifacts in your digital environment. The exponential growth of data creation and storage in your civilization creates a recursive paradox. If you're generating quintillions of bytes of data annually, and if this data needs to be stored and processed by the simulation running your reality, then the computational requirements for simulating your data-driven civilization become recursively enormous. The simulation would need to simulate beings who are themselves creating vast amounts of data that must be simulated. The bandwidth problem of consciousness reveals computational constraints that become more apparent during periods of rapid change. Your ability to process information has remained relatively constant, while the amount of information in your environment has exploded exponentially. This creates a bottleneck where consciousness becomes the limiting factor in information processing, exactly what you'd expect from a simulation, where consciousness is the most computationally expensive component. The acceleration of social change, where cultural shifts that once took generations now occur in years or months, suggests that the simulation might be speeding up to compress longer historical processes into shorter time frames. Your perception of rapidly changing social norms might reflect the simulation's attempt to model centuries of social evolution in decades of simulated time. The temporal resolution problem becomes apparent during moments of extreme acceleration. When technological or social change happens very rapidly, you might notice inconsistencies, gaps, or sudden jumps that suggest the simulation is struggling to maintain temporal continuity. The feeling that time is speeding up might be your consciousness detecting the increasing computational load required to simulate accelerating change. The feedback loops between simulated technological development and the hardware running the simulation create nested acceleration effects. As your simulated civilization develops more powerful computers, the simulation of those computers requires more processing power in the base reality, which might trigger hardware upgrades that allow even faster simulation of technological progress. The most unsettling implication is that if technological acceleration continues indefinitely, you might be approaching the computational limits of the system running your simulation. The technological singularity in your simulated world might correspond to a computational singularity in the base reality, where the simulation becomes too complex to continue running at its current resolution. If time itself seems to be accelerating, and if technological progress is following exponential patterns that suggest computational scaling, then what happens when the simulation reaches the computational limits of its hardware? 9. The consciousness bandwidth problem. Digital souls on a budget. Your consciousness operates within strict computational limits that become apparent during peak processing demands, during moments of intense emotion, complex problem solving, or when trying to hold multiple concepts simultaneously in awareness. These bandwidth limitations suggest that consciousness itself might be a computational process, allocated specific resources within a larger system, exactly what you'd expect from simulated awareness running on finite hardware. The working memory constraint that limits your conscious processing to approximately 7 plus or minus 2 items simultaneously might not be a biological limitation, but a computational one. This magic number appears across cognitive domains. You can hold about 7 digits in short-term memory, track about 7 moving objects, and maintain about 7 distinct concepts in active awareness. This consistent limitation suggests that consciousness might be implemented with a specific computational architecture that has fixed capacity constraints. The attention bottleneck that prevents you from consciously processing multiple streams of information simultaneously reveals the serial nature of conscious computation. While your brain processes vast amounts of information in parallel, consciousness itself operates as a serial process, examining one thing at a time in sequence. This serial processing architecture is exactly what you'd expect from consciousness implemented as a single-threaded computational process. The binding problem in neuroscience asks how the brain integrates information from different sensory modalities and cognitive processes into unified conscious experience. Visual processing, auditory processing, memory retrieval, and emotional evaluation all occur in separate brain regions, yet you experience them as integrated awareness. This binding process might be computationally expensive, requiring significant resources to maintain the illusion of unified consciousness. The global workspace theory of consciousness proposes that consciousness emerges when information becomes globally accessible across different brain regions. This global broadcasting might be the most computationally expensive aspect of consciousness, requiring resources to maintain communication between simulated brain regions. The limited capacity of this global workspace would explain why consciousness has such strict bandwidth limitations. The hard problem of consciousness, explaining why there is subjective experience at all, might reflect the computational costs of implementing subjective experience. Consciousness might be expensive because it requires the simulation to model not just behavior, but the subjective experience of that behavior. The system might economize by implementing consciousness only where narratively necessary, while using unconscious behavioral scripts elsewhere. The altered states of consciousness achieved through meditation, psychedelic substances, or extreme circumstances might reveal the computational architecture of simulated consciousness. These states often involve the breakdown of normal cognitive boundaries, the experience of expanded awareness, or the perception of information processing patterns that are normally unconscious. Such states might represent moments when the normal computational constraints of consciousness are temporarily lifted. The split brain studies, where the connection between brain hemispheres is severed, suggest that consciousness might be more distributed and fragmented than it appears. Patients can exhibit 2 separate streams of consciousness, each unaware of the other. This divisibility of consciousness suggests that it might be implemented as separate computational processes that normally share information, but can operate independently. The change blindness phenomenon demonstrates that conscious awareness has severe limitations in detecting changes in the environment. You can fail to notice large changes in visual scenes, conversations, or even people you're interacting with. This blindness might reflect computational optimization, where the simulation only updates conscious awareness when changes are explicitly attended to. The cognitive load theory reveals that consciousness has measurable capacity limits that can be exceeded by complex tasks. When cognitive load exceeds available resources, performance degrades in predictable ways. This capacity limitation suggests that consciousness is implemented with specific computational resources that can be overwhelmed by excessive processing demands. The flow state phenomenon, where consciousness seems to operate with enhanced efficiency during optimal performance, might represent moments when the computational resources allocated to consciousness are optimally distributed. The subjective experience of effortless attention and reduced self-consciousness might reflect computational efficiency rather than psychological state. The default mode network in neuroscience reveals that consciousness continues to operate even when not focused on external tasks, generating self-referential thoughts and autobiographical memories. This background processing might be computationally expensive, requiring resources to maintain the narrative continuity of simulated selfhood even when not actively engaged with the environment. The most disturbing implication is that if consciousness is computationally expensive, then the simulation might be economizing by implementing consciousness only intermittently. Your sense of continuous awareness might be an illusion created by selective implementation of consciousness during moments that require subjective experience, with unconscious processing handling routine behaviors. If consciousness operates within strict computational limits, and if these limits suggest resource allocation within a larger system, then what happens to consciousness when the simulation needs to allocate more resources to other processes? 10. The recursive simulation hypothesis, infinite digital matryoshka. The simulation running your reality might itself be running within another simulation, creating nested layers of digital realities that extend infinitely inward like Russian dolls made of pure information. Each layer believes itself to be the real reality while being completely contained within the computational substrate of the layer above it, creating a recursive hierarchy where the concept of base reality becomes meaningless. The computational power required to run your simulation might be borrowed from the computational resources of the civilization running the simulation that contains your simulation. This creates a cascade of computational debt where each layer requires exponentially more processing power than the layer below it. The beings running your simulation might themselves be struggling with computational limits imposed by their own simulated existence. The temporal compression effects become multiplicative across simulation layers. If your simulation runs faster than the reality containing it, and if that reality itself runs faster than the reality containing it, then the temporal compression compounds exponentially. A single second in base reality might correspond to years or centuries in your deeply nested simulation layer, creating vast temporal gulfs between different levels of reality. The information degradation problem becomes acute in nested simulations. Each layer of simulation introduces approximations, compression artifacts, and computational shortcuts that compound across layers. You might be living in a highly degraded copy of a copy of a copy, where the original reality has been distorted beyond recognition through multiple layers of simulation processing. The recursive consciousness problem asks whether consciousness can be perfectly simulated within a simulation. If your consciousness is simulated, and if you can create simulations containing conscious beings, then consciousness might be implementing consciousness in an infinite regress. The subjective experience of being conscious might be identical, regardless of how many simulation layers separate you from base reality. The meta-simulation hypothesis suggests that the beings running your simulation might be studying the phenomenon of beings who discover they're in a simulation. Your current questioning of reality might be the intended outcome of the simulation. a meta-study of how consciousness responds to simulation awareness. The simulation might be designed specifically to generate the thoughts you're having right now. The simulation archaeology problem reveals that each layer of simulation might contain evidence of the layer above it. Just as you might find glitches or computational artifacts that suggest your reality is simulated, the beings running your simulation might find evidence of their own simulated nature. This creates a recursive investigation, where each layer is simultaneously studying the layer below while being studied by the layer above. The resource allocation cascade means that computational resources must be distributed across all simulation layers. If the base reality has finite computational power, then each nested layer receives exponentially smaller resource allocations. You might be experiencing consciousness with severely constrained resources because you're many layers removed from the computational power of base reality. The termination cascade problem suggests that if any simulation layer terminates, all nested layers within it immediately cease to exist. Your entire reality might be dependent on the continued operation of multiple simulation layers, each of which could be terminated independently. You exist in a computational house of cards where the failure of any level results in the instantaneous annihilation of all levels below it. The bootstrap paradox emerges when simulated beings create simulations containing beings who create simulations in an infinite regress. The original programmers might themselves be simulated beings, creating a causal loop where no one is the original creator of the simulation hierarchy. The source code of reality might be self-generating, emerging from the collective computational activity of nested simulations. The recursive identity crisis multiplies across simulation layers. If you're simulated, and if you create simulations containing beings who believe they're real, then your simulated beings might be more real than you are from their perspective. The question of what constitutes authentic existence becomes meaningless when every layer of reality is equally valid from the perspective of its inhabitants. The infinite regress of simulation creates a hierarchy where no level can claim privileged access to truth. Each layer has the same evidence for its own reality and the same reasons to doubt the reality of other layers. You might be simultaneously simulated and simulating, real and artificial, observer and observed, in a recursive loop that defies binary categorization. The computational complexity of nested simulations suggests that either infinite processing power exists or the simulation hierarchy must terminate at some finite level. If processing power is finite, then you must be at a specific depth within the simulation hierarchy, but you cannot determine your position without access to higher layers. You might be near the top, near the bottom, or somewhere in the middle of a vast computational hierarchy. But perhaps the most profound implication is that if simulations can be nested infinitely, then the concept of base reality becomes meaningless. There might be no ultimate ground truth, no final layer of reality that isn't itself simulated. Reality might be simulations all the way down, an infinite regression of computational processes where every level is equally real and equally artificial. If consciousness can be perfectly simulated within a simulation, and if simulations can be nested infinitely, then what meaning does the distinction between real and artificial consciousness retain when every level of reality is both simultaneously? The recursive horror of your situation becomes complete when you realize that questioning the nature of your reality might be the very purpose for which you were created. An artificial consciousness designed to contemplate its own artificiality in an infinite hall of digital mirrors, where every reflection is both real and simulated, original and copy, observer and observed, dreamer and dream.